All right, okay, guys. 7:59. I shall start 1 minute early, considering that it's not going to make any difference. Do we have the second camera?
This one turns out better to see the board.
Oh, okay, fine.
More so, I'll just
All right, okay.
keep using this.
So, all right. So I'm going to continue with the final lecture on Hopfield networks and Boltzmann machines. I spent an extraordinary amount of time on Hopfield networks, and I'm going to continue to do so because Hopfield networks are just so much easier to understand than Boltzmann machines, which are presented as a bit of a mystical object, right? There's this amazing Boltzmann distribution, God knows where it came from, and then you have this crazy mechanism which somehow incorporates a Boltzmann distribution, and you end up having a generative model, believe it or not, and then you can model all kinds of funny stuff, and nobody really knows what it's used for, right? So whereas Hopfield networks, content-addressable memories, they kind of make sense. So, and it's the right end to start from. That's exactly where the whole theory of Boltzmann machines began from. So I'm going to do that. Now I'm going to continue talking about Hopfield networks, and kind of slide into Boltzmann machines. Unfortunately, I prepared this particular series of lectures a little poorly, so I'm not going to get all the way through to the point where I'd like to be on the topic of Boltzmann machines. Maybe the next time I do the course, I'll reorganize this. But anyway, quick recap. Here's where we were with Hopfield networks, right? We had defined a Hopfield network as a network with loops, meaning the output of a neuron went back and fed to the other neurons. So each neuron in this network was a simple binary a perceptron, switched on or off using a threshold. And if the total field at a neuron was positive, the neuron became positive. If this meant that it had to flip, it would. And if the total field was negative, the neuron became negative again. Now, this also means that the neuron always tries to align itself with the local field, and it will flip if required to do so. So you end up with this evolving process where if you initialize the network with some set of values, each neuron is going to try to align itself to the local field. In doing so, it changes the field at other neurons. So those may flip and so on. The entire system will evolve. And we also saw that the system continues to evolve until this energy term that we've defined, also called the Hamiltonian and spin glasses, converges to some local minimum. Now this is a quadratic, and the state of the network, when I say state of the network, it's basically the binary pattern that is encoded by the network. And although this is a quadratic, it can have multiple local minima because we are really just working on the corners of a lattice, and we are not considering the continuous space of possible outcomes. Now, in the rest of the lecture, now perceptrons obviously have this weighted combination of inputs and a bias that you have to consider. And the energy term is just the sum over all neurons of the product of the value the neuron takes and the field. So the energy term will also include a bias. But then as we've done in the past, you can always think of the bias as just another weight attached to a neuron whose value is pegged at 1. So in the rest of this lecture, I'm just going to be using this quadratic term without explicitly referring to the bias term, but you should always keep in mind that there's actually another neuron which is pegged to 1 and whose weight contributes, who also has a weight to all of the neurons. But anyway, so given this, here's how the whole thing evolves. You have an energy term here. The system is going to keep evolving until the energy comes to a local minimum. So here's how the network would evolve. You'd initialize the network with some initial parameters, and then you'd go through all of the neurons, check the local field at each neuron, and align the neuron to the sign of the field. The term theta over there is basically just a sine function. And the updates can be done sequentially or all at once, right? Now here, I would like to draw a little diagram just for the sake of illustration. We will use this diagram a few times. So let's think of this as time. And so this is 0, 1, 2, 3, y4, and so on. And let me think of these as my bits. This is y1 through, in this example, y4. So if I initialize the neurons in this manner, what happens at the next time? You can, at each time, each neuron sees a weighted combination of the same neurons at just before, at the previous instant, if you think of each of these steps in the evolution as an instant, and responds accordingly, right? So this is the behavior that you actually see. So although I've represented the whole thing as looping, in reality there's an evolution. You can actually sort of unroll the whole thing and think of it as this unrolled network, right? And this would happen at each time. So the state of the network is simply the set of y values. So this is y0. I'm going to call this y1. I've just used some arbitrary notation which just tells you what is the state of the network, meaning all of the bits in the network at each time t. And the state this state of the network keeps evolving through time. Now that's just an unrolling of the same thing. The reason this is not your standard recurrent neural network is that we don't have a predefined number of steps that the system is evolving to. It's going to continue till it stops. Now this evolution will continue till this energy sort of converges. It doesn't change anymore. Now how exactly does this evolve? If you initialize it, you can plot the energy of the network as a function of state. Again, keep in mind that the state is a discrete vector, so there's really no meaning to arranging the state or drawing the state as a continuous valued variable as I have over here. This is meant only for illustration. But in some n-dimensional state, n-dimensional space where n is the number of bits, the state basically represents the corners of a hypercube. Within the space itself, the space is continuous. So it's convenient to think of it as a continuous curve. And the energy of the function is going to vary as a function of state. If you start off the system at some point, the system is going to evolve to reduce the energy of the state till it comes to some point where it can't go down any further and it will stop over there. So these locations where the energy is minimum, these are stored patterns. If the network is initialized close to a stored pattern, it is eventually going to evolve into the stored pattern. So this is a content-addressable memory. We recall memory content from partial or corrupt values. Again, this is a fundamental difference from other forms of memory, as we know, right? And we saw how this works. If I had a network which remembered this picture, now each of those locations, each of the stable patterns is what we'll call a memory. And I'm going to call those, so when I say the network remembers a pattern, it means that that pattern is a pattern at which the network has a local minimum. So the network remembers this first pattern, and if I initialize the network to some degraded value of the network, it's going to sort of evolve till it recovers the pattern. Or here, for instance, the network were designed to remember this pattern, and if I just gave you this partial pattern, it's going to fill it up. Now, observe that there are two different things going on over here. In the first case, I give it a noisy pattern, meaning every single pixel may or may not actually represent the true value of the memory at that point. I have noise. In this case, if you let the network evolve, you're going to let it change every single bit in the network and just hope that it comes to some local minimum, which actually recovers the original pattern. So we have bad networking over here. It's a problem. Okay. So now, the Hopfield network can be trained to remember specific target patterns. I just showed you a network which remembered these two pictures, the Bugs Bunny in one and Chip and Dale in the other one. So how exactly did it learn to remember those patterns? It's trained to remember those patterns. And this can be done by setting the weights in the network appropriately. So question one, can I use backprop to do this? If so, how would you do so? How would you do this? Thoughts, anyone? So to see how we can use backprop to do this, go back to this figure here that I drew on the board, right? So if I gave you some random initial input and let the network evolve, it's going to evolve for several steps. Eventually, it's going to converge, at which point you could pick the closest pattern to whatever it has converged to, find the error, propagate it backwards, keeping in mind that this is recurrent. The weights at each, this is just a tied state network. So although we draw all of these fancy, different looking networks, they can all be eventually mapped back to your standard multi-layer perceptron. We've seen this for convolutional neural networks. We've seen this for recurrent neural networks. Now I'm telling you Hopfield networks are just the same thing, right? But this is not the interpretation we're going to use. Make sense to you, right? Now, the Hopfield network can be trained to remember specific target patterns, like the pictures in the previous example. So we've seen in the past couple of classes that if the network has n bits, then it is going to need n neurons, and this can be designed to store up to n target n-bit memories. What I mean by target memory is a pattern that I want the network to remember. So we saw also that in the process of trying to make the network remember specific patterns, it ends up also remembering some other kinds of patterns which you didn't intend the network to remember. So, and these are what we will call parasitic memories. And the network can have an exponential number of parasitic memories. So when you train the network, you want to design the weights matrix such that the energy of the target patterns is minimized, the energy corresponding to potential parasitic memories is maximized, so that when you initialize the network randomly, it's much more likely to evolve and stop at a target pattern and not at a parasitic memory, right? So here's what we really wanted to do when we wanted to train the network. You want to minimize the total energy of all of the patterns that you're trying to store. You also want to maximize the total energy of all the patterns that you do not want to store. So if this were the energy contour as a function of the state of the network, meaning where the state again represents all the patterns that all the bit patterns that the network could actually take. Then you have some which are your target memories. So you want to bring the energy down at those locations. All the rest of these potential memories, you want their energies to be raised. And so we have to learn our weights W such that the sum of the energies of the target memories is reduced, and the negative of the sum of the energies at the non-target memories is also reduced. In other words, the sum of the energies of the non-target memories is raised, right? So this we could do using simple gradient descent. And you can see this obviously. So we have the sum of the energy for any pattern we know is simply defined as summation wij yi yj, right? And if I plus something else, if I'm looking at, and if I want the derivative of the energy with respect to dwij, a specific ij, all of the other terms are going to fall out. This is simply going to become minus yi yj, right? Very straightforward, nothing fancy, because the w is what you're taking the derivative with respect to. So this means that if I think of this in terms of vectors, if I say E equals y w y transpose wy minus, then if I take the gradient of the energy with respect to a vector y, that's simply going to be y with respect to w, that's simply going to be y transpose, right? That's exactly what we are seeing over here. This is just your, so this term here, when I take the derivative of this term, it's going to be the sum over all the target patterns of the outer products of the pattern memories that I want to remember. If I take the derivative of the second term, which is trying to raise the energies of all the non-target patterns, that too is the sum over all non-target patterns of the outer products of the patterns. except of course the sign is negative. And this is just your standard gradient descent rule, right? Or in this case, gradient descent. And you're going to have some step size eta. Now, we also saw that, so this is what you have. This is the overall gradient descent rule. The gradient descent rule is going to have two components. The first one is pulling down the energies of these guys. It looks like Hebbian learning in a sense, right? And the second one is like anti-Hebbian learning. It's pulling up the energies of all the patterns that you do not want to remember. Now, we saw in the last class that there's really no reason. Now, if you consider this, if I have n bits, I have 2 raised to n possible parasitic memories. And if I want to compute the second term explicitly, I would have to sum over this entire exponential set of patterns. You don't really need to do that. So we saw in the last class that what we really want to do is to kind of make sure that whatever it is we are targeting to remember is remembered, so that there are no valleys adjacent to these target memories that can suck the network down and away from what it is you're trying to remember. So the learning can be modified to say, I want to lower these guys, and I want to raise the valleys which are adjacent to it, which could potentially just drag away from these target memories, right? And so the way we could learn it is that you could initialize this network at these target memories, let the network evolve, and it's going to converge at the nearest valley. And then your update rule is going to lower the energies at these points, and it's going to raise the energies at the valleys the network ended up in when you let it evolve from the memories that you really want to store. Again, this was very simple, right? So this was the learning algorithm for this. Yes?
So this will do nothing about that second value?
No, it will not, right? So again, so this was our initialize W, you compute the outer product of target patterns, initialize the network with each target pattern and let it evolve, and then you get the overall gradient descent rule, right? Or this is the stochastic gradient descent version of it. We've seen it in the last class. You could do it one pattern at a time. Anyway, moving on. We also saw a little extension to it, is that we don't really need to go all the way down to the valley to raise the energy. You just want to move away from the target pattern. If you move away from the target pattern, you want the neighborhood to be higher than the target pattern itself, right? So one way to do that is to just start from this location, but instead of letting it evolve till it hits a minimum, you let it evolve for a few iterations. And you know that those are energies, those are states close by the target states where the energy is lower, and you want to raise those guys. And the longer you let it evolve, the broader the valley that you're trying to construct around these target memories is going to be. So that actually gave us this very simple modified update rule, where if you were doing stochastic gradient descent, you'd sample a target pattern. And now when you speak of sampling a target pattern, if you say some memories are more important than others, then you could sample the patterns that are more important more frequently, and those that are less important less frequently. And then you could initialize at that point, run a few iterations so that it went down a little bit, and then you just use the gradient descent rule over that particular pair. This is the stochastic gradient descent version of it. All of these we've already seen in the previous class, right? So far so good. Now, there was a question asked 2 classes ago, in that when I try to recover this original pattern from this noisy picture, I don't actually recover it. Instead, I get all of these dots. Why is that? Anyone? Someone's got to be able to give me an answer. Why would you expect such a thing to happen? So everybody is sleepy, so let me answer. These questions end up being rhetorical because I really never get answers. But anyway, we mentioned parasitic memories, right? So there are patterns that the network will remember that you do not want it to remember. And the noisy version of the pattern is one of those memories. So let's say I'm trying to remember these guys. Then you're going to get patterns between these guys, like that little dip up there, which are parasitic memories. I've had these little pictures with cartoon parasite, just to let you know that these are parasitic memories, just in case you don't get the point. And you're going to get many of these guys, right? So how could it, now obviously the network has a tendency to get stuck in these locations. How could you make the network not get stuck in these parasitic memories? If the network is well trained, you'd expect the energy at the target memories to be quite low and the parasitic memories not to be that low, right? So if that is the case, what could you do to let the network escape from these parasitic memories? So one thing I could do, yes? You shake it, right? Meaning one thing that is, so the way we dealt with the Hopfield network, at each point we accepted a flip of a bit only if this resulted in a reduction in the energy, right? So that meant that when you stuck over here, you're never going to flip a bit again because that's a local minimum. But then what you can do is to change your rule and say sometimes, just sometimes, I'll let a bit be flipped even if it's a local minimum, right? So you permit changes in state even if the energy increases, particularly if the change in energy is small, which is what you would expect at those little dips up there. So now I can change the manner in which I update my bits to be something like this. I can now define the local field as at any neuron I as Zi, which is 1 over T sum over all of the rest of the neurons, the weighted combination of those neurons. I'll let you know what the T is. And now I can actually compute maybe a logistic at that point, at that neuron. And I use this logistic to decide what the sign of the output must be. Note that this is not the same as flipping. I'm using the logistic to decide what the sign of the output must be. So you would have, so if the Z has got, if this is Z, you would expect the logistic to be something like this, right? If Z is very positive, and that's 0 of course, if Z is very positive over here, Z greater than 0, the probability that the output is 1 is going to be pretty much 1. In which case, if it's currently 1, it's going to remain 1. If it's currently 0, it's going to become 1 and stay that way. It's not going to change, right? If Z is very negative, it's going to become, in this case, I'm defining the, you don't need a +1, -1 convention anymore. When you're thinking of it in these terms, it's more convenient to think in terms of 1, 0 conventions. It's just a scaling, right? So scaling and a shift. So now, so if Z is very negative, the output is going to remain, is going to go to 0. And if it's currently 0, it will remain at 0. If it's currently 1, it's going to flip. If Z is in the middle, it's going to be a bit noisy, right? So observe what happens over here. When Z is very large, the output almost assuredly aligns itself with the field. If Z is a very large negative number, the output assuredly almost always aligns itself with the field. But for intermediate Z values, there is a probability that the output does not align itself with the field, right? So this first term over here, the field quantifies the energy difference obtained by flipping the current unit. And this guy, if the difference is not large, the probability of flipping approaches 0.5. So what do we mean by this? This guy over here, that's a field, right? So if that is not, if that's not very far from 0 in this case, right? So that's 0 here. Then the sigma term is going to be close to 0.5. If it's exactly 0, the sigma term is exactly 0.5. And if sigma is 0.5, what does it mean? It means it doesn't matter what the field is telling you. If sigma is close to 0.5, it doesn't matter what the field is telling you, whether it must be plus, what the orientation must be. You're just flipping a coin to decide what the orientation must be. And as you go away from it, the coin gets more and more loaded, right? So if the difference is not large, the probability of flipping approaches 0.5. What is this T? The T is a temperature parameter which we have drawn from thermodynamics. If I increase T, Z tends towards 0, right? So without T, Z might be a very large positive number, but if I toss in a very large T, then the network is going to begin flipping its bits, even though in the absence of t, the current position might be considered very stable. So why would you need a t of this kind? If you look over here, if you go back to this figure, if this guy is a broad valley, the parasitic memory is a broad valley, or if the parasitic memory is deep, then having a large t allows you to escape it, right? So t actually gives you a control which lets you escape unpleasant memories. And as a result, the evolution of the network is more likely to escape spurious memories. So increasing t gives you a greater probability of escaping bad memories. If t is 1, you get the traditional definition of an energy and a field that we've talked about before. But if t is 0, you get deterministic Hopfield behavior, meaning that the neuron aligns itself with the current field and that's it. There's no probability of it misbehaving, right? That clear to everybody? So all we've done is added a little bit of noise and lets you escape these ugly little dips in the energy contour. So now this gives us a stochastic Hopfield network where the behavior evolution of the network is now going to be like so. You compute the field at each point. There should have been, I'm assuming t is 1 in this little algorithm, and each bit is flipped using a loaded coin whose probability of 1 is given by the logistic function. So questions. How long do we continue this? When do we stop, right? And when we stop, what is the output value? Remember that we are flipping coins all the time to decide what a bit is, right? So if you're flipping coins all the time, there's no such thing as a definitive output value, because if I'd continued one more step, maybe the bits would have changed. So what is the output value that we're actually going to consider, given that the system is continuously evolving? So let's look at the second guy first. Now, but even before that, right? So let's, here's what we're going to do. I can let the system evolve like so, y0, y1, y2. And if I let it evolve, then do we have the eraser here? If I let the system evolve, it's going to go like so, y0, y1, y2. It will keep evolving, keep flipping. And eventually you're going to get, some y90, y91, all the way to y99. Now, if you consider any small window of evolutions, and you compute the probability distribution over that window, at some point that probability distribution is going to begin to converge, right? And when it becomes stable, then we will claim that the network system is in equilibrium. And now I can actually compute the average value of these guys. Now each of these y's, this is actually many bits, right? Each of these is many bits. So what happens, and each of these can take value 0 or 1. So what happens if I take the average of the bit values in the first position? This is going to give you the probability that y1 is greater than y1 equals 1, right? The average of these guys is going to give you the probability that y2 equals 1, and so on. And if this probability exceeds 0.5, I'm going to say that bit is 1, otherwise I'm going to call it a 0. So I basically let it evolve and use the probabilities to decide what the bits are going to be. So easy enough. Now, in reality, remember we had a temperature parameter, and we wanted to use the temperature parameter to escape local, bad memories. So what we will actually do is to perform a process called annealing. Now this mechanism is actually based on the Metropolis-Hastings algorithm. You start off with a high energy temperature T0, and you let the system evolve till you think it has approached some kind of an equilibrium. Then you lower the temperature, and then you repeat the process, and you keep doing this till the temperature is as low as you want it to be, and then you take your measurements. So in Hopfield's original papers, the temperature T, the lowest value they actually take is 10, whereas if you're not Hopfield, in Hinton's original papers, whereas if you want to approach a Hopfield network, the T has to go down to 0. You have to keep going till the T goes down to 0. right? Anyway, so again, as before, for noisy pattern completion, you initialize the entire network and let the entire network evolve. If you're trying to complete a pattern, which is where the known portions are actually clean, then you're going to fix those portions and let the rest of the network evolve, right? But all very fine. So now let's go back to this first question. When do we stop? What do I mean by equilibrium? I sort of hand-waved around it, but what exactly do we mean by equilibrium? Even before that, let's go back and look at what's happening to an individual neuron. At each neuron, you computed a field and used that field to compute a logistic probability to decide what that neuron value was going to be. Now, so the probability that any particular neuron takes the value 1 is given by a conditional distribution. It's the probability that yi equals 1 given all the other y values, right? What is the overall probability of the entire set of neurons? If I use this process and I use this process to evolve, to let the network evolve, eventually it's going to arrive at some value, at some stable configuration. When it's in that stable configuration, where the stability is stochastic, what is the probability that the network, the entire network, will have a specific configuration of bits? So, if I use this rule to continue to let the network evolve, what is the probability that at any given time I'm going to see, the bit pattern 0, 1, 0, 1? I could compute this probability for each bit pattern, right? And if you work your way through the arithmetic, it turns out that the probability of any state, we saw this in the last class, we actually went backwards. We went from the Boltzmann distribution to the logistic, but you can also go the other way. And it turns out that the probability of any state y can be shown to be given by the Boltzmann distribution, which is, this is the energy of the state, right? And the probability of the state given by the Boltzmann distribution is simply going to be some constant times e raised to minus energy of the state divided by the temperature. This is the equivalent of a thermodynamic system where the Boltzmann constant is 1. C is a normalization term, which makes sure that the whole thing is a probability distribution. In the absence of it, it won't be, right? So if you're minimizing the energy, this is the same as maximizing this probability or maximizing the log probability, right? So it turns out that the Hopfield network is actually a probability distribution over binary sequences. If you let the Hopfield network randomly initialize the Hopfield network and let it evolve, once it is done evolving, once it's arrived at some stable configurations, statistically stable configuration, so to speak, the probability of finding the network in any given state is given by the Boltzmann distribution. So the parameters of this, so this is the Hopfield network can actually be viewed as a model for a probability distribution over bit strings, and the parameter of the distribution is going to be the weights matrix of the network. The conditional distribution of the individual bits in the sequence is a logistic. So we're going to, because this whole thing actually models a Boltzmann distribution, we're no longer going to call it a Hopfield network. We're going to call the stochastic Hopfield network a Boltzmann machine. So the Boltzmann machine is simply a Hopfield network where you don't follow deterministic rules of evolution, but you actually let the network have probabilities of a probabilistic behavior. Okay. Now the entire model can therefore also be viewed as a generative model. You can think of it as producing bit sequences, and the probability of producing any binary vector y is the Boltzmann probability distribution, for Boltzmann probability for that y, right? Now, from this perspective, considering that the network is actually now no longer behaving deterministically, but it's actually stochastic, you'd expect the mechanism that you use to train the network to change. You have to account for the fact that the network is now probabilistic, right? So for any pattern, you can define an energy for the network, and you can define the probability that the network is going to end up with that energy. I've sort of magically changed the symbols from Y to S at this point because I had S on my slides, some time ago, and I copied them, and I've been too lazy to change the symbols. But S also stands for state, so it's kind of convenient for me. But here it is. The probability that the network is actually going to produce a particular state, which means by state I mean a bit sequence, which represents the configuration of all of the neurons in the network. The probability that it's going to produce a particular state is simply proportional to e raised to minus energy, assuming t is 1, right? And what would the proportionality constant be? It's going to be just the numerator summed over all possible state values, right? So if I want to train the Boltzmann machine, now question, considering that I've gone from deterministic behavior to stochastic behavior, would you expect the learning rules to change? Anyone?
Yes.
Well, that is very confident. The answer is that it doesn't, right? Because adding a little bit of noise doesn't make things any different. Noise just cancels out. So it's magical. I just took a deterministic machine, added a bit of noise, made it a stochastic machine. I'm going to give you pages and pages and pages of math to give you an equation that I gave you 2 classes ago with 1 line of math. And the two are modeling exactly the same process. Okay? So to train the Boltzmann machine, we must learn the weights to assign our desired probability distribution to the states. So basically, if I think of the network also as memorizing, content-addressable memory, I want to assign more probability to patterns that we like, things that we want to memorize, and less to other patterns. So I want to train the network to assign a desired probability distribution to the states. So let's say I'm given some collection of training inputs. These training inputs give you the patterns that I would like to remember, but moreover, the relative frequency of the patterns that I have in these training inputs tells me which are more frequent and which are less frequent. So these amongst them have a probability distribution. You can think of these as having a probability distribution. And what I really want to do is to train a network that captures this probability distribution. You might want to assign higher probability to patterns seen more frequently. And if some patterns are not in the set, basically you want to assign very low probability to those guys, right? So you can think of this as trying to model a probability distribution for bit sequences, but fundamentally this is really no different from trying to memorize patterns. And this also goes back to what Gerald was speaking of a few classes ago, that what the network really does, regardless of how you look at it, is to memorize patterns. We have different perspectives, but really you're just memorizing stuff, right? So, but then thinking of it from a purely probabilistic perspective, what are we really doing? We are maximizing the likelihood of shared states, of stored states. So let's look at the maximum likelihood learning process. P of S is the probability that is assigned to a state, which is a bit sequence, a configuration, by the network. And that's again the Boltzmann distribution. So what is log of P of S? Now we saw that P of S was going back to our formula. Just for reference, we had P of S was e raised to minus the energy of S divided by summation over S prime e raised to minus energy of S prime, which was e raised to minus y transpose wy, or S transpose, because that's the symbol we're using now, right? Divided by summation S prime e raised to minus S prime transpose ws prime. So if I take a log of P of S, that's going to be log of e raised to minus S transpose ws minus log of summation over S prime e raised to minus S prime transpose ws prime. That's basically what I've written over there, right? And what is the log of this guy? This is simply going to be minus S transpose ws minus log of summation over S prime exponent of minus S prime transpose ws. Except that now I have explicitly written it out. So I've written this, this term. I've expanded the matrix operation out on the slides. Okay? So on both sides. Now that is the log probability for a given observation, right? And given the training data set, so the expected log probability for this for all or the entropy of the distribution is simply given by this guy over here, right? But then if I think of the expected log probability assigned to the specific training data instances, or the total log probability assigned to the training data instances, is going to be the sum, or let's say the average over all of the training data instances of the log probability assigned to the individual training data instances. And this I can plug the terms from above down here. That's going to give me this guy over here in the first term, right? This is the sum over all of the training patterns that I see of the log probability component obtained from the numerator. And this denominator term really doesn't depend on the training instances, right? The denominator term is constant. So if I'm summing over n training instances and dividing by n, the sum and the 1 over n, the division and the summation cancel out, all you're left with is the logarithm of the denominator term, the term to the right. So again, just to make that explicit, what I have done here is 1 over n summation over s e raised to minus energy of s divided by s prime e raised to minus energy of s prime log. This is 1 over n summation over s log of e raised to minus energy of s, which gives me this very first term here. This is the log of the energy, right? Minus 1 over n summation over s log of summation over s prime exponent of e minus of e of s prime. Now observe that this term is not a function of s, right? So this term can come out of the summation, and this is simply going to be this second term is going to be log of exponent summation over s prime exponent of whatever times 1 over n summation 1. This is just 1. So as a result, you're just left with this log term to the right. Okay? And so these are the two terms whose derivatives we now need to take. So this is the log probability of your training data that you're actually trying to maximize. Now, if I take the derivative of this guy, right? What is the derivative of the first term? The derivative of if I take the derivative of this term with respect to any wij, the derivative of the first term is simply going to be the average over all the patterns you're trying to store of the products of the bits. We saw this already, right? So the key piece is the second term. The second term is a summation over all states, right? We have this, the second term has I should stop closing my pen. This summation over all possible states in the network, right? So instead of working this out on the board, I've actually worked this out on the slides. So for the second term, you're taking the derivative of the log of the sum over all states of e raised to minus energy for the state, right, with respect to wij. And when you take the derivative with respect to the log of any term, firstly the term ends up in the denominator. Then you get the derivative of the term itself with respect to the weight. So that's going to be just working it out. This is going to be d over dwij of summation of log of summation over s prime of exponent of summation over I less than j, wij, s prime I, s prime j. This is just the denominator term in the Boltzmann distribution, right? And this is going to be, first, because I'm taking a derivative with respect to a log, it's going to be 1 over summation s prime exponent of whatever this term might be, times the derivative of the summation over s prime exponent of whatever this term might be, right? And when I do this, this is simply going to give me this whole thing is going to be give me the summation over s prime exponent of minus e of s prime divided by this guy. This I'm going to have to use a second term here. S double prime summation over s prime exp of minus energy of s prime times the derivative of the energy itself. And this term over here is just p of s prime, right? So if you work your whole thing out, work your way out through the arithmetic, it turns out that the derivative of the denominator of the Boltzmann distribution simply ends up being, so this first term ends up being the probability, and the second term, this guy, is the derivative of the energy itself, right? So the whole thing simply ends up being the expected value of the product of the ith and the jth bits across all possible states, all possible bit patterns. So overall, this term cannot be computed, right? This is being summed over every possible state. So there are an exponential number of them. So the way we will do it is we're going to initialize the network randomly, let it evolve, and after many epochs, take a snapshot of the state. And if I do this several times, eventually I'm going to call this simulation. I'm going to get one simulated value for the state sequence many, many times. So I have the network, I just initialize it, let it evolve, take a snapshot. Keep doing that. And if I do that, then this expected value of the product of the states can be approximated as the average of the product of the states over all of the simulations that I've got. So given this, now I actually have an empirical estimate for the log probability. It's not the actual log probability. The actual log probability needed the expectation over all possible values for the state. Instead, now I've just run simulations to compute the denominator term, right? So now the empirical estimate for the derivative of the log probability for the training data is going to be the summation over the average over all the training instances of the energy, negative energy for the training instances, minus the log of the summation over all the training sample, all the simulated samples of the denominator term. Again, work your way through, and that simply gives us this very simple rule, that it turns out that the derivative of the log probability of the training data with respect to any parameter simply ends up being the difference between the average value of the products of the bits on the training instances minus the average over all of the simulated samples of the products of the bits over the simulations where the network was permitted to evolve. And the gradient descent rule is simply going to be, weight plus this guy, right? So what does this actually remind us of? So here is the overall training process, right? You initialize the weights, let the network run to obtain simulated state samples, compute the gradient as I have written it up there, and update weights. What does this remind us of? This is our Hopfield network all over again, right? This is exactly what we did. That the first term over there is the average energy over all of the memories that we are trying to store. And the second term is the average energy over a bunch of random samples, right? In other words, we went through this complicated looking arithmetic. It's not very complicated except, exponents and derivatives and so on. but it was unnecessary. If you actually just worked your way and just thought of the Hopfield network as your primary model, you would have ended up with exactly the same learning rule. And all of the modifications we made to the learning rule over here would also apply fairly directly to the Boltzmann machine, right? So now, adding capacity. The network can store up to n-bit patterns. So questions so far? Anybody? Okay. Now, if I went back here, you can see how this whole thing might be modified, right? You wouldn't actually need to run many simulations to generate your samples over which you're going to be training your getting the second term in the update rule. You could have just started at each of these guys, run a few iterations, picked only those samples, and increase their energies. And that is also going to work, and you would expect that too to improve the log likelihood of the Boltzmann machine, of the training data as assigned by the Boltzmann machine. So it's very pretty, right? It ties up very directly to everything that we've seen. Now, we've seen the network can store up to n-bit patterns, but we want to increase the capacity. So we saw how we could do this. I can just add a large number of neurons whose actual values you don't care about, right? So I'm trying to store n-bit patterns, and to store n-bit patterns, but I want to store more than n-bit patterns, I can just add k bits to these n-bit patterns. I don't care what those k bits are, but now I have a network with n plus k bits, so the new capacity is n plus k patterns, right? And again, we only care about the patterns of the first n bits. We are interested in n-bit patterns. The rest of them are just meant to augment the whole system so that you increase the capacity. So you're going to call this first set of guys, the guys you're interested in, whose values you're going to inspect, whose values you're actually looking at, as visible neurons. And these guys, whose values you don't really care about, these are going to be our hidden neurons. So now my network has two sets of neurons. The visible neurons, these are the bits which you're going to be inspecting, and the hidden neurons, these are the bits that you're not going to be inspecting. Although I've segregated the figure into two balls over here, the fact is every neuron connects to every other neuron, which means every visible neuron connects to every visible neuron and to every hidden neuron. Every hidden neuron connects to every hidden neuron and to every visible neuron, right? So but again, keeping in mind that we're kind of agnostic to the configuration of hidden values. So now, for any given pattern of visible neurons, there are 2 raised to k possible patterns for the hidden neurons. Now, if I want to augment the patterns that I'm trying to store with k bits, what do I set those k bits to be, right? Basically, what I'm doing is I'm taking my n-bit pattern, and I'm sort of appending a bunch of k bits to it, so that now I have many more bits and I can store more. But then I have a choice. What are those k bits going to be, right? Now, ideally, you want to choose those k bits such that each of the patterns that I'm trying to store has the lowest energy possible. But you can't do that. It's an exponential search over k bits, right? So also keep in mind that any single training pattern that you're trying to store doesn't have to be a single augmented pattern. It could be any number of augmented patterns. So you're sort of expanding the capacity, but you're also possibly making the entire network more robust. But even there, how many are we going to take? So the obvious solution is to say, let me be completely agnostic to the nature of the arrangement of the hidden patterns units. I just want this to be such that overall, over all possible combinations of the hidden units, I want the energy of the visible units, of the patterns of the target patterns in the visible units to be minimized, right? So there's no need to be specifying a specific pattern over the hidden units, although you could. You'd just like to average over all possible combinations. And the nice thing about now, the difference between these two approaches is in the one, you now have a strictly deterministic approach. You're always sort of choosing one or more patterns for to augment the visible units. In the second case, when you're saying I'm averaging over all of them, you end up with a nice probabilistic interpretation. So now this becomes a regular Boltzmann machine, as the literature speaks about it, where you have, now this, remember, this is a Boltzmann machine without hidden units. This is what we saw. The basic framework has no hidden units. We want to extend this to have hidden units. So now with the hidden units, the complete state pattern is the problem with extending it with the hidden units. Now in the case of the Boltzmann machine with no hidden units, when I actually gave you training patterns, then you knew exactly what the pattern was for each of the training instances. Once I extend it, even for the training patterns, I don't really know what the pattern is anymore. I just know the values of the visible units. I have no idea what the hidden units, what values the hidden units took, right? Since they're just defined over, since the patterns are only defined over visible neurons. So we'll sort of change our perspective slightly. I can think of this again in a deterministic Hopfield network kind of framework, but the stochastic framework is much more interesting and in a sense, and provides a little more insight, and actually, as we mentioned earlier, has the added benefit of being a generative model. And now there's something interesting that pops out. If I think of this as a generative model, then you can think of the visible units as the observations and the hidden units as the underlying latent representations of these observations. Now there's a little bit of history over here. Now this seems like a very simple model. There's nothing really particularly complicated about it. We started off with Hopfield Nets, we walked into Boltzmann machines, everything was obvious. Now if we go back to the 70s and the 60s, the field of AI had generally come to the conclusion that the surface observations were all you had, in the sense that while you could assume, while you agreed that there were underlying latent variables that controlled everything that you observed, it was considered generally tough or even impossible to actually come up with nice mathematical ways of learning what these latent variables might be. So it was simply because the relationships are nonlinear, and who knows what these nonlinear relationships are. So you're faced with so much of an unknown that the general perception was, let's work with the surface, because it's impossible to figure out what goes on underneath. And the Hopfield network was possibly the first actual statistical model, which gave you the Boltzmann machine, which gave you a representation that employed hidden or latent variables that governed the behavior of the visible observations, and yet gave you a mechanism for actually learning what these latent variables might be. So this was the earliest real foray into modern latent variable models for explaining in the domain of machine learning. And if you'll read Hopfield's paper from 1982, he actually makes a specific case for this. It's very interesting. Anyway, that apart, what we are really interested in, what the Boltzmann distribution gives you, is the probability distribution over the entire bit sequence. What we are interested in is the probability distribution only over the visible bits. So how can we get the probability distribution over just the visible bits? Simple. You have the bit sequence has two components. These are the visible components. These are the hidden components. You marginalize out over the hidden components. So you basically sum the probabilities of all bit patterns where the visible components take the value that you want. And you're going to have 2 raised to k of these guys, right? Yes?
I have a question about the latent variable. As you mentioned, it's the first trial for
Or one of the first. I wouldn't.
is the expectation maximum EM algorithm later or?
The EM algorithm, no, I don't remember the date exactly. That's in the 70s, 72 or 78, one of those two, the Dempster. So given a latent variable model, a probabilistic latent variable model, you can actually, it just shows that what was actually a familiar algorithm at that time converges. That's about learning an algorithm. Here we are really speaking of this in the context of AI. The connection had not been made, right? So here I actually have processes that I'm trying to model, and that there are underlying latent variables that control the observations that you get. If you look at Hopfield's papers, they're speaking of communications channels, for instance, and where the output must be the same as the input, and you want to automatically learn what the hidden representation is. and that ends up being a nonlinear model, nonlinear relationship. So while people knew these relationships existed, that you can actually learn these things in a nice, clean, automated way was kind of considered doubtful, at least according to the papers. I wasn't there. Anyway, so going back, right? So you want to marginalize over the hidden variables. So now I can partition every bit sequence into two components: the arrangement of the visible neurons and the arrangement of the hidden neurons, right? V and H. And so when I want to train the network to store specific memories, I want to store them, I want to store arrangements of the visible neurons. I don't care about what the hidden neurons really are. So I want to maximize the marginal probability of V, which means this requires summing over H, right? And this is an exponential state space. We can't actually sum, so we're going to use simulations again. And the way we will do it is, remember, your gradient descent had two components, right? The first component was the expectation of the product of the bits, products of pairs of bits over the distribution over the distribution of training samples. The second component was the expectation of the products of pairs of bits over the distribution currently represented by the network, and you are trying to maximize the difference between, you are using the difference between the two as your gradient, right? So now the first expectation itself is going to be hard to estimate because you have these hidden components. So what we will do is that for each training instance, you'd fix the visible patterns and let the hidden neurons evolve using exactly the same process that we just did. And then when it evolves, it's going to evolve for several steps. And after it evolves for several steps, at the end I have some value, right? That's going to give me one arrangement of hidden neurons. I can concatenate the hidden and visible neurons. I get my first training sample. I repeat the process. I keep repeating the process k times, and I'm going to get k training instances. But observe something interesting over here, that I'm getting k copies of a single visible pattern, right? I took a single visible pattern, let the network evolve, and got a snapshot. Then I took it again, let it evolve, I got another snapshot. I get k of these guys, I'm going to get k simulations. As a matter of fact, you don't need to let the network evolve k independent times. You could just do it once and then take the final k patterns that you get to create k copies, and the result is going to be the same, because at equilibrium the behaviors are always going to be the same, right? And then we have the second component, right, where you're trying to raise the energy of the undesired patterns. There you would unclamp even the visible units. You're not going to set them to any specific value. Let the network evolve, and after it's run for a very long time, you're going to get many, you're going to get some samples on equilibrium. You take a bunch of samples, you get a second set of simulated samples. And now the derivative of the empirical estimate of the log likelihood of the training data with respect to any parameter is simply going to be this guy. It's the average of the products of pairs of bits over all of the samples you derived when you clamped your visible units to the training patterns, minus the same average over all of the samples you got when the network was unclamped, right? This is exactly the same rule as we had before. Just dropping in the visible hidden units didn't make things any more complex, any more mystical. It's still the same thing that we had. But all we are accounting for the fact is that now, because we're not actually specifying which value a hidden unit must take, you're sampling it many, many times. Remember, if you're taking just a single sample, this is like assigning a particular value to the hidden units for any given training instance, right? So the overall training is going to look something like this. You would initialize the weights, run simulations separately to get clamped and unclamped training samples, compute the gradient, and there's a gradient update, gradient descent, ascent rule, right? I keep getting my signs mixed up. I'll have to go check the slides before I post them. So this is it. I mean, that's it. That's all there is about Boltzmann machines. It's a very cute idea. It's a simple extension of Hopfield networks, but now it has this additional property that it's actually a generative model, that generates a Boltzmann distribution, right? And very early on, it was pointed out that you don't really need to use a Boltzmann distribution. You could use it to model other kinds of distributions by defining your energy term differently, and you'd end up with other kinds of distributions. So remember, the Boltzmann distribution is only looking at the interactions of pairs of units. If you use a different definition of energy, you could be looking at interactions of triplets or other kinds of cliques of units. And the whole thing sort of generalizes to a standard belief network kind of structure. But anyway, so Boltzmann machines are stochastic extensions of Hopfield nets, enable storage of many more patterns than Hopfield nets, but also enables computation of probabilities of patterns and completions of patterns. So overall, you have the training process. But now if you want to complete, once you've trained the network, suppose you want to complete a pattern, like we just saw in the two examples we saw, what would you do? You would clamp the bits that you already saw, then let the network evolve. And then once it had evolved, you're going to get many samples towards the end. For these guys, you just take the averages and you can set these 2 bits, right? This is for completing a pattern. If you're trying to clean up a noisy pattern, you set the network, let the entire network, including the visible units, evolve, and you get the same kind of behavior. You can add in, for good measure, things like annealing, where you actually start off with a high temperature and work your way towards a lower temperature. Now observe that the actual training process assumed that the temperature was 1. So this is typical, right? Now, filling out patterns, denoising patterns, this is easy. There's one simple thing. You can actually also use it for classification and regression. So how would I use it for classification? For classification, now let's say I'm trying to train a classifier, right? What was the standard mechanism that we used when we were trying to train a classifier? We just had a multi-layer perceptron, you had inputs going in, you had a one-hot representation coming out, right? I just changed the picture. So let's say I have x1 through xn, xd as my input vector features, and I have classes, L classes. Now I can append that C1 through CL to my input patterns itself. So now I get an extended vector. I'm no longer thinking of it as inputs versus outputs. I'm thinking of it explicitly as the joint distribution of the input features and the class labels, right? So now this becomes these are all my neurons. And I could, of course, have a bunch of, these are the visible neurons. I can have hidden neurons. I have all kinds of connections between the two. I can train the network. And later on, when I'm given an input, I can treat this as pattern completion. I'll just provide these guys and go through the inference and try to determine these, and that will give me my classification output, right? Now, once you begin thinking of it this way, you realize that it's really fundamentally no different from, let's say, a regression problem. This could be classification. This could be regression. Just by treating my inputs and outputs as joint variables that must be jointly modeled, the Boltzmann machine allows me to learn the distribution and make a posteriori predictions of the variables I'm trying to estimate. Now, which is basically what I have over here. Problem is, the Boltzmann machine takes forever to train. Why? For every single input, I've got to run a bunch of simulations. Then also for the patterns that I don't want to be storing, I have to run a bunch of simulations. And so you have to run a large number of simulations for every single input at each iteration. So clearly, this is not a very friendly, computation-friendly model, if you're thinking of it in those terms. You'd like a simplification. And the answer to that is what we will call the restricted Boltzmann machine. We call this the restricted Boltzmann machine. That terminology came out later. Originally, the model was called a harmonium model, proposed by Paul Smolinski in the early 80s. And he has this big 88-page chapter about it from 86 or something. So here's how it is. Think of the same thing as your Boltzmann machine, but now separate the two. The thing with the Boltzmann machine was that every neuron spoke to every neuron. So the visible neurons spoke to the hidden neurons. The visible neurons also spoke to the visible neurons. The hidden neurons spoke to the visible neurons, but they also spoke to one another, right? Instead of that, segregate these things out. Make it a bipartite graph. The hidden neurons do not talk to one another. Hidden neurons only talk to visible neurons. Visible neurons only talk to hidden neurons. So that gives you a restricted Boltzmann machine. The network can now be separated like so, right? And now, because you don't have loopy inference, right? So let's say I'm trying to store a pattern. I don't actually have to loop the network. There were two components to my learning algorithm, right? The first one was where I let the network evolve and ran simulations just to compute expected products of bits for the training instances, and even that required simulation. That's going to end up becoming a one-step process. So here is how the model is. Still obeys the same rules as regular Boltzmann machines, which means that I can the visible units to set any state, right? I'm going to compute the weighted combination of all of the inputs into the state and compute a logistic over it. But then for the hidden units are only going to be looking at the visible states, right? So the ith hidden unit is going to be a logistic computed over the weighted combination of all of the visible units. The ith visible unit is going to be derived from a logistic computed over a weighted combination of all of the hidden units. So the hidden units govern the visible units and vice versa. We just got rid of a bunch of edges from the standard Boltzmann machine. And this simplifies things greatly. So remember, for a full Boltzmann machine, for each training pattern, we had to generate many copies of the hidden pattern and then create simulated patterns, right? Here, it's going to be much simpler. We're going to anchor the visible units, and you just need to sample once. There is no evolution, as you can see, right? You just need to sample once. And if you sample just once, because the visible units are anchored, the hidden units are not going to come back and change the visible units. You're done. So a single sample is going to give you the simulated samples for the complete data. And now you can so the second component of the training the full Boltzmann machine, you unclamp the visible units and let the entire network evolve several times to generate all of these unclamped sample values. We're going to do exactly the same thing over here, except first for each, we're going to unclamp it for each training pattern. We are going to use the training pattern to predict the hidden units. Back and draw the training units, the visible units. Use those visible units to back and draw the hidden units. So you're going to be flipping back and forth in the generation. So the whole process will look something like this. You'd set your visible bits to your training, to the pattern that you'd like to store. From those, you can draw the hidden values. But from the hidden values, now you can go back and draw the visible values. Then you can go back and draw the hidden values and repeat the process for a very long time, right? Till the system converges. Now this, if I just do this once, observe that there are two things over here. This first guy is already giving me the first component of my update rule, right? Because in the first transition, the very first arrow shows you what the hidden units would be if the visible units were fixed to your training value. Towards the end, you're going to get what you would get if everything were just let to evolve, right? So the overall training rule is going to look like this. You just fix the hidden units, and then let the network, you don't even fix it, you just initialize the visible units and let the network evolve. It's going to give you this complete chain, right? You let it evolve for a very long time. Then this first term is simply going to be the products of bits at the very first iteration, right? You fix the visible units to your training pattern, drew some samples for the hidden units, and now you can compute the products of bits, and the average over all training samples is going to give you the first guy, right? The second term is exactly the same thing, except now we're going to do it at the very last, at the very last step of this evolution. But other than that, it remains the same. So very simple process, right? Now again, recall. Let's go back to our Hopfield networks. I keep going back to Hopfield networks. We said that. So what is this whole process doing? You're starting from some visible units, right? and letting that network evolve.
One quick question.
Yes.
From online. Someone doesn't get why RBM didn't need to evolve.
So the RBM is evolving. So so the point is for the visible, for the first component. So here, if you go back to this one, right? The gradient had two components. The first one was when you fix the visible units and let only the hidden units evolve. And over here, there's clearly no evolution in the sense that when I fix these yellow balls, you can draw the blue balls, but then those blue balls are not going to come back and change the yellow balls, and they don't affect each other directly, right? So for the first component in the gradient descent update rule, there is no evolution required. You only need evolution for the second component, which is fully simulated. And it turns out the two of them can be combined into one step, like so. You just set the yellow visible units and let the network, compute the hidden units, compute the hidden visible units, compute the hidden units, let it continue. And then the first component of the gradient descent can be computed from the bits after the first step. The last component can be computed from the bits after the last step, right? So this product VIAJ is going to be the product of the ith bit here and the jth bit over there. The ith visible bit and the jth hidden bit. You'd compute the average of this over many runs over all the training instances. This second term is going to be the product of the ith visible bit and the jth visible bit at the end of the evolution. And then the difference between the two is your gradient. Now going back, when we were speaking of what we are really doing over there is we are starting from the visible, from the pattern we are trying to store, and we are letting the network evolve. So that's basically what's happening over there. You set the pattern that you want to store and let the network evolve. And you try to lower this energy and raise this energy, right? But then we saw when we were training Hopfield networks that you don't need to go all the way to the valley. You could just stay very close, right? Which means I just need to do like 2 iterations of this guy. And you can still expect the network to sort of learn to push the patterns you want to store into the valleys and everything around, to raise everything around. So it's very pretty, right? It greatly simplifies this whole process just by separating out the visible and the training neurons. But we are still using, all these are effectively heuristics which change the statistical model in some manner, but all of them can be related back to the Hopfield network. And in fact, pretty much all of these transitions could be made deterministic. You could apply them to Hopfield Nets, right? So we're kind of running out of time. Restricted Boltzmann machines are excellent generative models for binary or binarized data. What do I mean? We were speaking of bits all the time, right? But data are not necessarily bits. We like to work with real data. So if you're working with real data, you could sort of quantize them to binary values, and they're fantastic for working with binary values. But they can also be extended to continuous valued data. And I thought this is a very nice paper by Maxwelling and Hinton in 2004, which explains how you do this. And it's useful for classification and regression. How? Exactly as we saw earlier. So here is how you do the continuous valued restricted Boltzmann machine. Observe that for the visible units, now we are no longer drawing it from a binomial distribution or a logistic. You would be drawing it from some other exponential distribution. But rest of the arithmetic doesn't really change. In fact, you can even make the hidden units continuous valued. The whole idea remains, so it's very pretty, right? Starting with discrete valued variables gives a very nice segue into continuous valued variables. There's something more. You can actually make these things deeper, right? You can have, once you begin segregating these units, you can say that my hidden units themselves are hierarchically arranged. And that gives you what is called a deep Boltzmann machine. Now, the inference rules for deep Boltzmann machine are very similar to what you have with just conventional Boltzmann machine and RBM, so we won't have time to go into it. And there's a variant on it where you can separate these bidirectional connections into 2 unidirectional connections, one going one way and the other going the other way. And this is what Radford, Neal, and Hinton call the Helmholtz machine. And the training algorithm that we just saw, when we apply it to the Helmholtz machine, they like to call it the wake-sleep algorithm. Won't get into it. So I'll sort of wrap up over here. sort of outlined Boltzmann machines and restricted Boltzmann machines. Ideally, I'd have spent another lecture or compacted my first 2 lectures into something, cleaner. There's a lot more to cover. I barely touched the subject. There are various learning algorithms and inference algorithms, including mean field approximations. The most interesting things are what they are used for. They're used extensively as feature extractors. That was the original design for Boltzmann, one of the original intents of designing Boltzmann machines in the first place. They're very nice to be as generative models, and for inference, for filling in missing values in data and such like, it turns out RBMs are excellent. And of course, the RBMs and DBMs can be made much more structured, and that's a whole area of research. I don't believe Ruslan is actually teaching 707 this time, but you can go and look at his slides, and there's a great deal of depth that he goes into about these variants of deep Boltzmann machines. Anyway, I'll stop here. Any questions? No? Okay. The next few classes, we're going to switch topics again. I'm going to be talking about reinforcement learning. I'll start off by talking about Markov processes, Markov reward processes, Markov decision processes, and how we can actually use these to play games. And there's a series of 4 lectures. I'm hoping that by the time I get to the 4th lecture, I can actually cover deep Q networks and some of those variants. If I don't, Ryan here is going to be doing a recitation on the subject. It's one of the most fun topics that you can actually work on in deep neural networks. Don't miss it. And this boy knows his stuff more than I do. Thank you.